Hello everyone, I'm Hyungjin Kim. Today, I'd like to talk about motion-based calibration between multiple LiDARs and INS with rigid body constraint on vehicle platform. Multiple sensor calibration became important since variable sensors are kept in autonomous vehicles. Right picture shows neo-autonomous vehicle platforms equipped with various sensors. As a typical method, marker-based calibration system could not provide reliable results. And also, the calibration results are changed so often. Therefore, we need auto-calibrations for multiple sensors. This paper proposed a robust and reliable motion-based calibration method for multiple LiDARs and INS with graph structure optimizations. The graph structure has three constraints: matching-based, motion-based, and rigid body constraints. This paper also demonstrates the performance and quality in real self-driving car platform. The left picture shows the conceivable motions and matching-based constraint. The matching-based constraint can be measured between appearance-based sensors such as LiDAR at specific time. Motion-based constraint can be measured by sensors' motions during the movement. If we have diverse sensor motions, all sensors can be calibrated. But the movements of car platforms are very limited. It has only straight and curve motions. Therefore, we added another new rigid body constraint to overcome these limited motions. Matching-based constraint is very similar with a constraint of postgraph slam. However, the nodes are not increased even though the new measurements are arrived, because the nodes represent here a sensor location instead of vehicle pose. Only new constraints are added on the same nodes over and over again without adding any new nodes. Motion-based constraint is based on hands-eye calibrations, which is AX equal to XB. The constraints can be measured by motions of sensors. In this paper, one motion is from the INS and the other motions from the LiDAR odometry. As I mentioned before, the vehicle motions are limited, so this constraint has some ambiguity. For example, we could not measure the Z elements if we don't have any up and down motions. However, the car platforms usually moves on the flat ground, so it has only few up and down motion. Therefore, we add an extra constraint called rigid body constraint. We assume all sensors are kept on the rigid body, thus we added the Euclidean distance constraint between sensors. We do not add orientation or XYZ each element in the rigid body constraint, because it is hard to measure the orientation of sensors, and XYZ each element also depends on the orientation of sensor. All these constraints are added in one graph structure, and then it is solved by optimizations with nonlinear least square method. Then finally we can get calibration results for each sensor. The proposed method is very flexible to apply various sensor systems. Some constraints may not be measured at specific node or time based on the sensor system and configurations. However, graph structure scheme can handle sensor calibrations even though some nodes are not connected at specific time. This picture shows an example of a sparse graph structure. The proposed method tested and verified with a KD dataset with a comparison method. The comparison method is utilized by multi-sensor calibrations without a graph structure optimizations. The result shows the superiority of proposed method. Also, the proposed method is demonstrated with practical autonomous vehicle platforms owned by NIO. The results are tested map quality by counting number of the voxelized points. The results are better than the comparisons for all 5 drives. This video shows the quality of the proposed auto-calibrations by comparison of raw data. The left one shows the raw RTK GPS result without calibrations, and right one shows with calibrations. On the left side, you can see duplicate ramp and trees, but right side you cannot. so we can recognize calibration is well performed. This video shows auto-calibration results of all 5 LiDARs. The extrinsic parameters of all LiDARs are calibrated at the same time by optimizing graph structure. As you can see in the video, all sensors are dramatically calibrated when the vehicle has curved motions. Thus, we made the 5 test drive as infinity loop shape and tested. The calibration results of all 5 are very similar. This means the results are very reliable. The point cloud of this video shows LiDAR odometry results by accumulated points from all LiDARs, so we also can see the quality of LiDAR odometry. This video shows how each LiDAR contributes to generate the point cloud map. In our autonomous car platform, we have 5 LiDARs: left, right, rear, roof, and top. Left, right for yellow and cyans, rear for blue, and roof and top for green and red. The gray point cloud represents the accumulated all points in the drive from RTK GPS pods with calibrated results. All point clouds are very clear and there is no duplicate objects, so we can visually see the map quality. We also conducted road tests to generate a high-quality map with calibrated sensor. All sensors are pre-calibrated from the infinity loop test. The dense point cloud data is generated from calibrated 5 LiDAR sensors with RTK GPS. You can see clearly trees and road signs and traffic lights. Please enjoy the map quality. Thank you for listening. If you have any questions, please let me know. Thank you.